Let's start with a Fourier transform example. So at the end of the last lecture, we got the formula for the continuous time Fourier transform. And the first thing I want to do here is give you a couple of definitions for useful functions that we'll be using in this course. First one being the rect function. So we define this as, we just call it rect of t, and it's defined as being 1 when the absolute value of t is less than or equal to half. 0 elsewhere. So it's just this very simple function like this. Little rectangle, right? Now, the area under the integral of this function is 1, so it's a nice unit function. We have some other functions, the unit step functions, which also have use. And these ones are 1 for positive t, non-negative. Okay, so this one looks like this. Okay, that's the unit step function. Notice that you can write the rect function in terms of unit step functions. For example, we could do rect of t equals a time-shifted unit step function. Should be that's a half there. Let me write that better. And then subtract off another time-shifted unit step function. Okay, so what is this? If we graph this over here, here's t. The first term is simply, let's put 0, let's put minus a half. So what we have are a unit step function, the first one shifted to the left by a half. Second term is another unit step function shifted to the right by a half. Oh, that's ugly. All right, and when you add these, of course, you get what we want. Goes up, over, down, and over. So 0 everywhere except between negative half and half. Now you notice I'm being a little bit casual about one thing. Maybe someone noticed and would have a complaint that under my definition these aren't actually true. Nobody wants to complain? Okay, the value at exactly negative half and plus a half is inconsistent here. In my definition of rect, I said it's 1 at those boundaries. I put these little circles to kind of indicate that it's a 1 there. Okay, and if I do this subtraction, it would be 1 here, but it would be 0 here. So they're not technically the same, and so I'm just going to be casual. In continuous time functions, changing the value at one point in time is inconsequential, and anything will do. Okay, so I don't really care that these aren't actually equal. Here's a now in discrete time we do care about individual points, right? Because discrete time is only a bunch of individual points. So we care about every individual point in discrete time, but in continuous time we don't care about any individual points. Another way of using step functions to create a rect is to say that equals, that also you could say equals the product of two rects. Now notice I have different rects that I'm using here. The first one is the same one, but the second one is flipped horizontally. So this is the product of, let me go down. Okay. maybe like this. Okay, so this is the product of a rect like this and a rect like this. And when you multiply them, this is all that remains, right? Okay. Now, let's now do the Fourier transform of this rect function that we've defined. Okay, so the formula I gave last time said that x of f should equal an integral over all time of the function we want, that we're interested in. In this case, it's rect t, e to the negative I 2 pi ft, integrated over t. So that's the Fourier transform. Let's do this calculation. Notice that rect, how do we integrate something with a rect times something else? Well, rect is a nice function. It's just 1 in some interval and 0 outside that interval. So to incorporate that into the integral, all that does is change the limits of integration to negative a half to a half, because this function inside is 0 everywhere outside that interval. Okay, and inside that interval, it's e to the negative I 2 pi ft. So now we're getting to functions that we're used to integrating. Okay, so this equals negative 1 over I 2 pi f, okay, times this, integrated from t equals negative a half to a half. All right. Now that formula only holds actually if f doesn't equal 0. Right? If f equals 0, I have an invalid formula here. So let's just do it 2 cases. So it's that. And if f equals 0, then we can go substitute it in and do that integral directly. If f equals 0, this is just 1 in the integral. So the integral should just be 1. Right? Okay, so this is f not equal to 0, f equals 0. Okay, so let's simplify further. And that equals, now up here, plug in negative half and half, and what we're going to get is negative 1 over I 2 pi f. And here, when you plug in a half, you get e to the negative I pi f. No t anymore. Pi f. And then minus e to the I pi f. Does that look correct to you? Check myself. Yep. Okay. Of course, that was for the first case. Still 1 in the second case. And finally, I would rather interpret that as a sinusoid, okay, because we have a difference of 2 complex exponentials. So that equals sine. I've got a negative here I'll bring in, and you can see that it actually just equals sine of pi f. Sine of pi f over pi f. Okay? Or 1. Now, one thing to notice here is that conveniently, this function up above, okay, true for all f not equal to 0. If you take the limit as f goes to 0, what would we get? So sine for very small values, sine of pi f is just close to pi f for small values. Yeah, so what we get is 1. The limit as f goes to 0 is 1. And yet we know for f equals 0, we should get 1. So in fact, we won't write this anymore as 2 separate cases. We'll just say, we'll just call this is sine of pi f over f, where for the value of f equals 0, you're just using the limit. Okay. Now, we have a name for this function. This is defined as sinc of f because it, in fact, is such a nice and important function in signals. This is the sinc function. Has anyone encountered the sinc function before? Oh, nobody. All right. So let's just look at what the sinc function looks like when we plot it. There's f, 0. At 0, it's got a value of, well, let me just put some of the integers here first. Okay, has a value of 1 at 0. It's a sinusoid that's getting tapered off as f gets large. In fact, it looks like this. Now, usually you think of sine as an odd function. It has anti-symmetry, right? But so is pi f. So when you divide by pi f, you get something that's even. You get an even function. Okay? And notice for every integer value of f, this is going to hit 0, except for the value f equals 0. That's the only one where it doesn't cross 0. Okay? So these 0 crossings are kind of nice. The sinc is actually a very well-behaved function in the sense that it's easy to remember what it does. It crosses 0 at every integer. It's this wave-looking thing. Okay? So put a 1 here. Okay. So that's sinc of f. Sometimes we'll also look at sinc of t. Same thing in the time domain. So this is the Fourier transform of rect of t. All right. Now, I want to solidify this. Well, gosh, things are behaving funny here. I want to keep comparing, for now, the Fourier transform to the Fourier series because we've sort of taken some time to understand the Fourier series. Now we're just jumping into a Fourier transform that looks similar in formula, but I want to, again, just reiterate how this is related to the Fourier series. So, suppose we were using a Fourier series to look at the rect function. Of course, the Fourier series is only made for periodic functions. So let's look at rect at the periodic extension of rect. Let's take a cap t greater than 1 and let x of t be the periodic extension of rect. So the idea is here's t, here's 0, minus a half, and let's let cap t be something over here. Okay, here's minus cap t. And this signal x of t, it's a rect, but it's a periodic extension, so it goes up to here. It has another rect centered at cap t, another one at negative cap t, and so forth. So it's periodic like this. Okay. Now, if we look at the continuous time Fourier series of this, okay, what we get is that ak, the coefficients, are going to be 1 over the period. It's this integral. Okay, so there's our formula for the Fourier series. First thing I want to point out, and I didn't mention this before, but turns out you could calculate the Fourier series coefficients by integrating over any one period. So I've always expressed this as an integral from 0 to cap t. Okay? But in fact, any one period will give you the same answer for this integral. You can check that if you don't believe it. Go do some example. We could integrate from, for example, negative cap t to 0, or from negative cap t over 2 to cap t over 2. Any interval we want that's of width cap t will give you the exact same answers for this formula. Okay, so what that means is that's because x of t is assumed to be periodic, right? Okay, so this equals 1 over t. In our case here, we're going to it'll be nice to just say this is an integral from negative t over 2 to t over 2 of rect t. I'm substituting that in. I should put that up here too. Let's say rect t. All right. Oh, it's not rect t. Sorry. It's our periodic extension of rect t. That's why I left it as x. Okay, x is the periodic extension of rect t. However, so I'll put it here and then I'll change it in a moment. Now that we say we're integrating from cap t over this interval, right, then we won't hit any of the extra rects, right? There's a rect in the middle and then there are copies of it. But those copies are outside of the integral, so they don't matter. So I can go ahead and just replace that with rect. Okay? So these are the coefficients for this Fourier series. And notice now that we can just say that equals 1 over cap t. Now look, that integral is exactly the integral for the Fourier transform of rect. We just did the Fourier transform and we had the same expression. Now it's not by coincidence. Right? It would have been the same had we used something other than rect. It still would have been the same. So this is exactly x of evaluated at this frequency here. So it's the Fourier transform expression with that plugged in for f. Okay, since I see some confused looks, I'm going to go right up to the Fourier transform exercise we just did. Here's the expression for the Fourier transform. And when your signal is 0 outside of an interval, you can just put those limits in the integral, right? And so this is the expression. And notice the difference between this and the Fourier series, aside from those limits of the integral, is that we have an f here instead of a k over t. So really, we're just evaluating this function at k over t. Of course, we also have a 1 over t out front down below. Okay, we have this 1 over t, so I'll keep that. Boy, Peter wants to be very sensitive today. All right. Don't want blue. Okay, so those are the coefficients that we get. And we just calculated what the Fourier series was for rect. So this is 1 over t sinc of k over t. So no matter what period we use, these are the coefficients we're going to get. So notice this is simply a sampling of this sinc function that we already looked at. So we have this sinc function. All right, it crossed at all the integers. And all we're saying is these Fourier series coefficients are simply sampling this where you're sampling it at 1 over t, 2 over t, and so forth. So depending on what t we use, we'll get different Fourier series coefficients, but they're all related in a very simple way. They're just samples of the sinc function, okay, at different points. The bigger you make t, the more finely you're sampling this sinc function. All right, so this is like A0, A1, A2. Okay, now, of course, remember that the inverse, the synthesis equation, so we recover x of t by doing a sum, right? We sum over all k of a sub k e to the I 2 pi k over t, t. All right? That's how we get back. And notice that now what I want you to think about is, what if we let this cap t go to infinity? If we let cap t go to infinity, then x of t is really just going to be like the single rect function, not periodic, right? Because periodic extensions are way far away. What happens when you take a sum like this and you say, well, we plug things in from above, that's 1 over t, whoops, that's 1 over cap t, I'm just plugging in, sum over k, and then it's sinc k over t. E to the I 2 pi k over t, I'll put that in parentheses too, t. Notice that this whole function in the sum is in terms of k over t, and we have a 1 over t out front, and you might recognize this as an approximation of an integral. All right, this is it's a Riemann integral approximation. So that means that in the limit, this should go to the integral. Sinc of f e to the I 2 pi ft df. Okay, so the point of all that was just to show that if you take this limit of letting the period go to infinity, then you find that there's a simple relationship between the Fourier series coefficients and the Fourier transform, and in fact, you get back an integral that should reverse the Fourier transform. Okay, so this says that the inverse Fourier transform, rather than a sum, should be an integral. So you should get x of t equals the integral from negative infinity to infinity, x of f e to the I 2 pi ft df. And that's the formula I gave last time. Okay. The remainder of this lecture will be about understanding some properties of this Fourier transform. But I should also give you a definition for the the discrete time Fourier transform. So to summarize these formulas, you already have the continuous time Fourier transform, which I won't write again. It's already in this lecture and the previous lecture. But I'll go fill that in after the lecture, so you'll have it in your notes. The discrete time Fourier transform is very similar. You have that x of f is going to equal the sum from n equals negative infinity to infinity of xn e to the negative I 2 pi fn. Okay? And the inverse is that xn equals the integral from negative half to half of xf e to the I 2 pi fn. Okay, maybe it is helpful for me to put the continuous time ones here again just so that you can make a comparison. So I'm going to rewrite this. Here's what you have for continuous time. You have that x of f equaled the integral from negative infinity to infinity, xt e to the negative I 2 pi ft dt. And you had that x of t equaled the integral from negative infinity to infinity, x of f e to the I 2 pi ft df. Okay, so we have now our continuous time and our discrete time formulas, both forward and backwards. We would call this the inverse. These are the inverse transforms to get back to the time domain. If you want to, you can think of this as the synthesis equation, like we called it, synthesis equation for the Fourier series. Okay, it's the way of getting back from your frequency components back to the time domain. Okay, now the continuous time Fourier transform is, wait, hold on a second. Okay. We've talked about the continuous time Fourier transform. We did an example. We took the transform of rect. We got sinc. Discrete time, notice the formula is almost the same. For example, we've just had to change an integral to a sum because you're summing when you have a sequence, right? But notice that frequency, even in discrete time, f is not discrete. You're still talking about a continuum of frequencies here and here. It's only discrete in time, okay? Because to get back to xn, you actually integrate over frequencies. You're not summing over some sequence of frequencies. The summing was for Fourier series. Fourier transforms always have a continuum of frequency, okay? But there's one other difference here. Does someone notice another difference between the continuous time and discrete time formulas, besides the fact that we already mentioned a sum was an integral? But what other difference do you see? How about the limits of integration? Yeah. So here we're integrating from negative half to half, right? Why is that? Well, because just like we saw with the Fourier series, in discrete time, xf is still periodic. Due to aliasing. So for the same exact reason that we had periodic coefficients in discrete time, we have a periodic xf with period 1. Okay? And you only have to integrate, to invert it, you only integrate over one period. Just like we discussed a minute ago, in fact, you could integrate over any one period. It doesn't have to be negative half to half. You'll get the same exact answer to this integral if you integrate from 0 to 1, from negative 1 to 0, or whatever interval you want. Okay, but often you just choose to do negative half to half. So let's look at some properties. And this will serve two purposes. We're going to talk about what we really want to do. Most of the properties we'll look at will say if you manipulate your signal in some way, say you move it, you shift it in time. We'll talk about these simple changes you can make to a signal, and we'll say, what would that do to its Fourier transform? Okay, what does that do to its frequency components? But the first thing is actually not of that flavor. We'll talk about duality, and this is simply observing that hold on. Yeah. This is simply observing that this continuous time Fourier transform, it looks the same forward and backwards. The forward formula and the backward formula are the same up to that minus sign. Okay? So that gives us a duality in the sense that let's write that. All right. Now this is specifically continuous time Fourier transform. The discrete time one has a sum and an integral, so that makes it a little bit different. But the continuous time one, they're both pretty much the same. That means that if you let y of f be the Fourier transform of x of t, if that's the Fourier transform of x of t, then that means that y of negative t is the inverse Fourier transform of x of f. Okay, if that looks a little bit funny to you, then I'll express it another way. Express that same statement as the following. If x as a time signal, when you take a Fourier transform of it, you get some, I often will use capital X for its Fourier transform, some function of frequency, right? Well, duality says that then if you take that capital X, but instead think of it as a time signal, and do the Fourier transform again. In other words, apply the Fourier transform twice. You applied it to X to get capital X. Apply it again, right? That you'll basically be doing an inverse. You'll get back to X flipped horizontally. So it won't quite be X. It'll be almost the same as X originally. It'll just be time reversed, okay, flipped horizontally. So doing a Fourier transform twice is almost like doing a Fourier transform and then doing its inverse. The inverse and the forward Fourier transform are pretty much the same thing in continuous time. They just end up constituting a flip in time. So we'll check this. And here's how you check any of these Fourier transform properties. Although, yeah, so what we'll do is say, let's introduce a new name for a signal. It's called z of t. Actually, I could just use y. Okay, so let's say y of I'll just do it the way my notes say it. Let's say z of t is the inverse Fourier transform of x. Yeah, I'm using the second equation here. So we have x interpreted as a frequency signal, e to the I 2 pi f t df. And we notice that a lot of these variables are just so-called dummy variables. They could be swapped. For example, I could easily swap this t as long as I change all the t's on the right and left-hand side. Still an equality. So I can make this x of, for example, negative tau. Let's plug in negative tau there. And nothing changes except for that I change t to negative tau on this side as well. Tau, put the negative out front. df. Okay. Now there's another dummy variable, and that is what we're integrating with respect to is f. Oh, I dropped an f from up here. We're integrating with respect to f. Let's make that a t. There's no other t's in this formula now, so integral x of t e to the negative I 2 pi ft dt, and now we see that's the forward Fourier transform equation. We started with the inverse, and now we turned it into a forward Fourier transform, right? And so that is simply the Fourier transform of x of t. Okay, so z was the inverse Fourier transform of x of f. And we're saying that when you flip it in time, you get the forward Fourier transform of x of t. So that proves our duality statement. I guess the only confusion here is thinking about what these equations mean. And I'll leave that to you to just think through. What does this duality mean? All right. For one application, we can use it right now. And we can say that we already learned that rect of t, when you take a Fourier transform of rect of t, you get sinc of f. All right, we calculated that. That means that if you have sinc of t as your time domain signal, and you take a Fourier transform, you should get rect of negative t. That's what duality says. You should get rect of negative t. By the way, rect is even, so that equals rect of t. So in this particular case, you get just a really simple duality. Fourier transform of rect is sinc. Fourier transform of sinc is rect. That's what duality tells us. We don't have to do a calculation here on sinc to get rect. We can just use duality. In fact, sinc of t is a very useful signal, as we'll see later on. We'll be using sinc of t a lot. Okay. Other applications of duality are that any property we derive for the Fourier transform will be a property for the inverse Fourier transform as well. Okay, so you'll just keep that in mind. These properties are very symmetric. All right. Let's look at the time scaling property. Okay, and first of all, let's just make sure we solidify what a time scaling is. Okay, so suppose x was an arbitrary signal, and instead of x of t, you want to now look at x of at, where a is some real number. First of all, what does this do to your signal? Let's say a was 2. What happens to your signal? If a was 2, it's going to pull it together horizontally, right? It's going to like shrink it in time. If a was a half, it's going to spread it out in time, the opposite, right? If a was negative, it both flips it in time and possibly stretches or expands it. All right. So, all right. So what you're going to want to do is be familiar with all these manipulations, what they are, and then we're going to want to see what does that do. And so if we have like this type of signal, let's just do a simple cartoon signal, and we look at, and if that's x of t, then x of at will be something like that, where it goes to 1 over a. Is that correct? I think so. Okay. Yeah. So you just squish it or stretch it. Okay. So let's start by assuming we know the Fourier transform for x of t. And we want to say, how does it change if we're looking instead at x of at? Does anyone have a hunch? What should happen to the frequency domain if, let's say, a is 2? Okay, so you've squished things this way by 2. What would you expect to happen in the frequency domain to x of f, capital X of f? What? Okay, would it also be squished this way? It would be stretched, because think about it. A frequency gets increased as you squish it this way. Think of a sinusoid. Bring it closer together, you increase its frequency. So you'd expect in the frequency domain, things get moved to higher frequencies. Let's see that happen by formula here. So we'll take the Fourier transform of x of at. And now let's change variables. Let tau equal at. And this is going to be the integral from negative infinity to infinity. And now it's going to be x of tau. But up here we get e to the negative I 2 pi f over a tau d tau. Okay. Now there's one thing to check here. Oh, sorry. There's a 1 over a out front, right? Okay. So this is how you do a change of variables. Pretty simple. However, there's one thing we have to be careful about. That is that what are the limits of integration now? Well, they still should be infinite. However, if a was negative, they're flipped. So we do have to pay attention with whether a is positive or negative, because if a was negative, it would be from infinity to negative infinity. We can handle that by bringing a negative 1 out front if a is negative, right? And that's simply going to be this. So it's equivalent to say, that it's 1 over the absolute value of a. So that's, in fact, the truth. That handles the limits of integration. Okay? And this equals 1 over absolute value of a, x of f over a. So that's our property. Okay, this is the time scaling property, that the frequency domain gets spread out if the time domain gets shrinked, or vice versa. They do the opposite. And also there's just a coefficient that affects things that can become more intuitive as you think through examples. Okay, so there's our first property, and it's nice. It kind of corresponds to what you would hope would happen. Let's do linearity. We saw when we did other linear transforms, we mentioned linearity. Let's just mention it again a little more carefully. So this simply says linearity always has two requirements to call something linear. It's you should have the so-called superposition property, and that says that if, let's say, whatever the operation is, whatever the arguments are, it doesn't matter. There's always a general definition of linearity. It says that if you put in two arguments added together to whatever your operation is, that you should just get the sum of that operation on each one separately. Okay, that's superposition. And then there's a scaling property that's part of linearity as well. You need both of them to call something linear. And that says that if you scale by, it doesn't have to be a real number. It could be complex if you're in a space that deals with complex numbers, that it should be a times g of x. Okay, so you can actually check both of these properties just by putting in something of the, you'll see what I do right here. If you put in, let's check the linearity of the Fourier transform. What is going on? Let's check the Fourier transform. We'll put in Fourier transform of a x of t plus y of t. Now this checks both properties at once, the scaling and the superposition. All right. We want to check that this equals a times the Fourier transform of x plus the Fourier transform of y. All right. And this is going to be pretty clear because we know that integrals are linear. So this is going to be ax of t plus y of t plugged into the Fourier transform equation. A by 2 pi ft dt. And by linearity of integrals, we get that that's a integral of x of t plus integral of y of t. Which is ax of f plus y of f. Okay, so we've checked linearity. It's a linear transform. Oh, I want to point out a couple things. I keep skipping some details I want to mention to you. One is that we've calculated one Fourier transform so far, rect and sinc, right? Even though our signal is real, the Fourier transform can be complex. In general, it will be. All right, it will have a magnitude and a phase, for example. We might want to look at it that way. But in this case, it's not. Okay, rect actually becomes a real function sinc. That's because it's a symmetric. It's even. A real even function will always do that. Okay, but I don't want you to get the false impression that we're always going to get real answers to our Fourier transforms. We won't. We just happen to get it in this case. What else? Well, let's go on. Okay, another property. And this is the... oh, I remember what else I wanted to mention. I want to mention that we're doing these derivations for continuous time, but they actually hold for discrete time as well. However, let's not say that here. For later properties will hold for discrete time. In your problem set, you're going to look at a similar property to time scaling for discrete time. The problem is time scaling doesn't always make sense in discrete time. I mean, it won't be well defined. Okay, but you'll do that in your problem set. Linearity, of course, holds for both discrete time and continuous time. Okay. How about a time shift property? Okay, so consider what does it mean if we look at x of t minus some constant. I'll use tau as that constant. Okay, so we have some signal x of t. and we look at x of t minus tau, that's the same signal with a time delay. It's a shift horizontally, right? So here's t, 0, 1. Let's say here's our signal x of t. Then x of t minus tau is something like this, where this is tau, and that's tau plus 1. So if this was x of t, then that's x of t minus tau. Okay, that's what it is. Now, what would you expect this to do in the frequency domain? So you have some Fourier transform of x of t, and now we want to know what's the Fourier transform of x of t minus tau. Are there any expectations intuitively? How should the frequency components change? What? They shouldn't. Great. That is a great answer. Well, you'll see that that's on some level that's correct here. Okay. So let's take because you'd say, well, if you just shift your, let's say it's some sound. You're using MATLAB. You're doing a DFT. If you shift things in time, you have the same frequencies there, right? Okay. Although it's got to change somewhat because we know we can invert this Fourier transform. So let's do this. Okay, now, again, do a change of variables. But this time, just let u equal t minus tau. There's no scaling constant for that change. So you get x of u e to the negative I 2 pi f. And you get a u plus tau up here, du. And we can separate that into two exponentials multiplied together. And one of them doesn't depend on u, the argument of our integral. So it comes all the way out front. So this becomes e to the negative I 2 pi f tau. And then we still have the integral here. Okay? And now we recognize that integral. We've just changed t to u. It doesn't matter. That's the Fourier transform of x. So we leave this out here. Whoops. Yeah, f tau. And then we get capital X of f. So it did change. It got the frequency components got multiplied, but notice that the change is sort of only affects one part of x. This has magnitude 1 and phase of course, negative 2 pi f tau. So a phase that depends on frequency. Okay. So what this means is you have not changed the phase. Oh, sorry. You have not changed the magnitude. Whoops. The magnitude doesn't change. And the phase becomes whatever the phase was of x of f. Okay, remember, this is a function of frequency. The phase differs as you move along frequency. But the phase of your Fourier transform actually ends up with a linear shift. If you think of negative 2 pi tau is a constant, tau is just some constant that you shifted things by in time. This is a linear function of frequency. So the new phase of your Fourier transform is the old phase before the time shift, plus something that increases linearly with f. Okay? But the magnitude hasn't changed, so that's why you said it shouldn't change, because you're thinking of the magnitude when you're thinking all of those same frequencies are there. The phase tells you when they happened, and this is how it changed. I know we're out of time, and I think that was my last property. Oh, I had one more, but we'll do it next time.